Okay, ladies and gentlemen, welcome back to the class. I am Konita, your master of ceremony. How are you today? Yes, you look fine, you look fresh. Did you guys have enough sleep last night? Of course. Did you guys have your breakfast? No? Don't worry, because today, in this morning, we will have our breakfast, our yummy breakfast together. In quote, our yummy breakfast in quote. Yeah, you already know what I mean. Yeah, I think you already know what I mean. Back then in the first day, we got a lecture about Introduction to Cryptography by Dr. Dia from Universitas Gajah Mada. She mentioned about something yummy. And the keywords are nano, micro, microscopic, super tiny particle, yeah, something like that. So that's our breakfast. Introduction to quantum physics, which will be delivered by Dr. Pekik Nurwantoro. Let's give him applause. Okay, to Dr. Pekik, please welcome. Enjoy, guys.
Good morning, participants. Hopefully, all of you are in fit and well conditioned. What I will talk today concern about the quantum physics. Maybe this topic mostly beyond of your previous background or knowledge, except one or two I know from physics department. But last Monday I asked some people. They said that most of the participants here from mathematics, or at least not from physics. But it's okay. If we talk about the quantum physics, yeah, some people agree that this topic is not easy. Yeah, this topic is quite difficult to understand. Yeah. Even in some textbook, in introduction, usually there is some remark from some physicists, for example, from Feynman. There is a quote from Feynman. Feynman is special because in physics, he is well known for his expertise to deliver some difficult subject in easy manner. So when he said that quantum physics, so when he said that quantum physics is difficult, and he's not sure whether some people really understand the quantum physics. It means for us, common people, it's okay if we don't understand. So this is not an discouraged quote, but to encourage all of us, some reader, some student, that learning about the quantum physics, understand about the quantum physics is difficult. That's why we must do everything to understand the basic principle of the quantum physics. Even for lecturer, he must try to find how to explain in easy way. Yeah. So this is what I will talk today. Our course line maybe can be divided in three parts. the first part about the overview, we will talk about the two possible type of computing and future potential breakthrough. When we talk about the quantum physics in this room, we think that we will use or we will try to understand the basic principle of quantum physics in order to understand the quantum computing, quantum cryptography, and etc. So, not all the subject of quantum physics will be given today. Just some points which are important in quantum computing, quantum cryptography, etc. Also, our scope in this talk just mentioned some examples, some important examples, which maybe are correlated with the quantum computing or quantum cryptography. Actually, after this talk, maybe there is another talk about the quantum computing and etc. Our second part will talk about a brief look of quantum physics. I just follow the common ways in many textbooks. In order to make easier the topic of quantum physics, usually we just confront it to other subject, which is classical physics, where we consider the classical physics is easier because classical physics concern about our daily life. Yeah. So hopefully, because of our daily life, we easy to understand because our perception based on this daily life, this experience. So in second part, I will talk about the classical physics versus the quantum physics. And the last part of our talk about the basic concept of quantum physics, we will give the illustration and the important thing, especially in mathematical point of view, is about the postulate of quantum mechanics. The word of quantum in quantum physics or quantum mechanics can be rooted from the word of quantize quantum, because when we look at the atomic scale, microscopic scale, some experiments shows that some observables are shown in not continuous way, but in discrete ways. This is differ with our daily experiences, because if we talk about our position in time, we can talk about our position in arbitrary value. This is usually happen in our daily experiences, but in atomic scale, in microscopic scale, some observable just has value in certain value. For example, if we talk about the energy cannot have zero value. So it means because of zero value of energy, that particle cannot rest in, just move every time. And what speed he move cannot in arbitrary value, but in certain value. For example, in 1 meter per second, 2 meter per second, but not in 1.5 meter per second. This is in our atomic microscopics. So it's completely different with our daily experiences. So I consider that the difficult part of the quantum physics because of two things. One, because of the physical background underlying this theory. The second thing about the mathematical tools to do the computation. Let's see in first part, the underlying framework of the quantum physics. Classical physics-based conventional computing or conventional or classical computer, actually based on using classical phenomena to perform the computational tasks. If we talk about the addition operation, multiplication operation, that's related with addition and multiplication in classical phenomena. A building block of devices is the so-called bit 1 and 0 value. Spirit value 1 and 0, not in mixed state. Quantum physics-based quantum computing is different because it uses the quantum phenomena to perform the computational tasks. A building block of devices is the so-called quantum bit, in short, qubit. This is actually the superposition or mix of 0 and 1. So we talk about the probability of the value. For one cases, the value is superposition. But in quantum mechanics, it is required, it is fundamentally required that every object, every state are in superposition condition. The sum of many states. To represent the actual state, we will look or we will measure. So there is no classical counterpart of this phenomena. It's completely different. And this is why the quantum phenomena is difficult to understand. Because in our daily experiences, we never experience about this perception. If we know the initial condition of particle of, for example, the condition of sphere in that disk, in we know the initial condition of the electron, we will not know the exact condition in later time. What we will know only the probabilistic condition in later time. Actually, even Einstein was not agree with this point of view. Einstein think that quantum mechanics is not complete theory. But unfortunately, he didn't know how to complete it until he died. And we still use the quantum mechanics because until this time, there is no single experiment which show that the quantum theory is wrong. Actually, all of our devices, our small devices, computer, etc., based on this quantum mechanics. How about the future, when we can use, or some people can implement that phenomena? Some experts believe that the potential use of basic quantum computing, for example, in this area. There are many other areas, but usually we talk about these three phenomena. The first phenomena based on the superposition of state, which is the character of quantum physics, not classical physics. Because of the superposition of state, they lead to what the so-called quantum parallelism. The parallelism is a nature of the quantum computing. But in classical computing, we must do some certain procedure to make parallelism happen. But in quantum computing, parallelism is automatically happen. That's why some problem which require a highly costly computation, for example, how to factorize the prime number, which is the key point of the cryptography, etc. Also, a short algorithm hopefully will be replaced by this quantum algorithm. The second one related what the so-called quantum entanglement. This is also one aspect of one effect of quantum mechanics, which is no what they call the classical counterpart. There is no analogy in our daily life. Entanglement. Quantum entanglement, that's why. Because of the quantum entanglement, it opened the possibility of teleportation, potence, error correction, and the other. I will, hopefully I will give an example to just illustrate why this happened. If there is an entanglement, then it is possible for us to do some weird thing. And the second one is the composite qubit system, where when the system is composed by many qubits, then there is a possibility for us to get the exponential speed up of quantum phenomena. the speed up is exponential, it's not linear. This is this remark has been given by Feynman, who think that if we try to solve the quantum problem, maybe it is not possible if just use the classical computer. That delivered by Feynman around 40 years ago. Why? Because in quantum problem, the number of states is very huge. And if we try to solve this problem, we must with the power of classical computer, which has the very speed computation time. So we must use the supercomputer. But we know that the speed of technology to make classical computer has very high speed. It's in linear time. The natural problem in quantum physics in exponential number of states. So it's not sweet. So that's why maybe Feynman said we must try to find out the other type of quantum computing. And that's why we call it the quantum computing, not classical or not conventional computing. Just to illustrate what I just said about the problem in quantum physics. Let's consider a quantum system consists of n spin half. In quantum physics, there is a particle which has spin. In simple way, this is just up direction and down direction. Up direction represent number half and down direction number minus half. So when we talk about the material, physicists can model as the configuration of spin. So the stable state of that spin system will be given by the orientation of the spin up and down. So mathematically, one of the model in spin system just the summation of this number. For example, here plus half minus 1. So this is will is and this is a simple model. When there is a contribution of external disturbance, for example, magnetic field, there is an extra term which is the summation of the spin and its neighborhood. This is some value which represent the external field, external magnetic field. So we can consider that this system actually just the summation of the number of the value of the spin. So how to find the stable state? We must try what is the minimal value of all of the summation configuration. So there are so many configurations. That's why when we have n spin half, the operator, the measurement, can be represented a certain matrix having order or dimension of 2 power n times 2 power n. Because there are two possibilities. That's why when there are two spin, so this is 2 and another spin 2, and n spin will be 2.n. So if we will use the vector 2.n, that's why the operator here may be in the matrix 2.n row and 2.n column. So the element of matrix will be 2.n and 2 power n. Let's take n is 50. 50. When we calculate, this corresponds to approximately 10.30 metric element. Let's see the data of the last supercomputer in China, who has the operating performance at 33 teraflops, equal to 33 times 10.15 floating point operation per second. So this simple, very simple problem is not huge material, just intermediate material, because only 50 spin. In real case, there are more than 50, 1,000 million and etc. But if just 50, we need 33 times 10.15 floating point operation per second. The speed of the supercomputer right now equivalent to 10.24 floating point per year. So if there are so many configuration, 10.30 can be operated by same summation by 10.24. That's why just to solve that simple problem, we need 10.6 years using the supercomputer. So it's not possible. That's what Feynman said. It is not possible to solve the quantum problem in classical computer. So let's take the second point. Phenomena in classical physics can be summarized in this effect. When we see the dimension or the scale, the macroscopic scale usually more than 10⁻⁻⁶ or micrometer. In our daily life, this thing around 10 centimeter. So this is classical physics. In classical physics, also be characterized by the deterministic or predictable event, not probabilistic event in quantum physics. Predictable, because if know the initial condition, mathematically, we will know the next condition by solving that model. For example, using the Newton law with equation, for example. Observer are outsider of the observed system. It means, principally, we can try to minimize the effect of the measurement, because the measurement is outsider. It is not part of the system. So, principally, we try to minimize the measurement in order our result will be in high accuracy. In our daily life, this is possible. The fourth is local correlation. One particle, principally, physically, just give the effect to its near particle. It is difficult to understand if someone said this particle will influence the second particle outside this building, except there is very high interaction on the particle. But in ordinary interaction, we can say that if there is one particle here, it will interact with other particle also in this building. This is the classical phenomenon. This is called the local correlation. The last part is just common sense, because our perception based on our experience. So it's okay when someone explains something. Usually we will understand, especially if there is a data for it. But phenomena in quantum physics, that is microscopic or atomic scale, less than 10⁻⁻⁶ meter. For example, the atom has dimension of 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ Very, very small part, small scale. In this world, in this microscopic scale, some experiments show that the probabilistic or unpredictable event will occur. The second thing, the observers, someone who do the experiment, always part of the system, are insider of the observation. That's why in quantum point of view, there is no way to ignore the process of observation. If we want the result of the system, so we must do the experiment. But when we do experiment, or we will try to find out the result of the system, actually we just has disturbed the system. Because every our action actually part of the system. So this is quite difficult to understand, because our daily experiences, our perception will say that our action can be minimized. In quantum physics, it's not possible. The other thing is non-local correlation. This is called the entanglement. Even Einstein, everyone know Einstein, the great one in physics, physicist. Yeah. Even Einstein does not believe about this phenomenon. Yeah. It is called the EPR paradox. EPR, Einstein, Podolsky, and Rosen. They together write a journal just to oppose this phenomena. But experiments show that this is true phenomena. Yeah. So in this case, Einstein is wrong. Non-local correlation, entanglement. And the last part is seemingly contradictory or paradox or weird result. Let's see the difference between the classical physics and quantum physics in mathematical model point of view. We took two phenomena in classical physics. Yeah. The first one, wave equation. That's actually the second order differential equation in time and space. So you represent the propagation of the wave. If we can solve that equation, so we will know the behavior of the wave in time and space. The second one is the Newton law of motion. The first one represents the wave. The Newton law of motion represents the particle. If we know the initial condition because of the second order differential equation, so by using the initial condition, we will know the next event of this particle. So in classical physics, wave and particle are spirit entities. In quantum physics, Schrödinger, Heisenberg, and etc. Yeah. propose the equation, the so-called the Schrödinger equation in the form of differential equation, but the other correspondingly to this equation, what the so-called the Heisenberg picture or Heisenberg representation. This is actually the metric form of the Schrödinger equation. Two type of model actually is equivalent, are equivalent. In quantum physics, we know that the wave and particle are complementary entities. We can talk the electron as a particle, but at the same time, we can talk electron as a wave. Also, if we look at the light, we can talk about the wave as expected in our daily life. But in quantum physics, we can talk about the particle of the light. It is called photon. The wave and particle is the same. Some people call this phenomena as wave-particle duality. So the question, in what condition electron as a particle or electron as a wave? In quantum physics, electron as a particle if we do experiment as experiment, and electron will represent as a wave if we do the experiment as a wave. So depend of our disturbance, depend of our measurement. So this is rather difficult to understand in our daily experience. So some people say it's rather weird. It's difficult to understand. But in the fact, the experiment agree with this phenomena. Let's move to the theory about the quantum physics. The other part why the quantum physics is difficult because of the mathematical tools underlying this theory. If you look at the Newton law, mathematically we just did the differential and integral to solve that equation. But in quantum mechanics, there are many mathematical tools to solve the problem. We need the metric, algebra, linear algebra. We need a differential equation. We need Fourier transform and etc. It's not common in many physicists. So usually we start with what we call this as postulate, just a statement. But later we prove that that statement is beneficial because that's agree with the experiment. So we just take it. No need for us to question that why and how that question works. The postulate one state concerning about the state space. In microscopic point of view or in quantum physics point of view, every occurrence, every physical system will represent with the so-called the wave function, the state function. In Dirac notation, we call it the state cat. This this abstract entity, in mathematical point of view, actually can be considered as the space in Hilbert's space. N-dimensional vector space, which in this space is defined the inner product. So the value, the certain value of the state can be given by the operation of inner product. So there is no need to consider the real function, real metric. We can use the complex metric, complex function. Because if we need a real value to compare with the experiment, the operation is the inner product of this vector. So we talk about the n-dimensional complex vector space. Postulate 1 state that the quantum system is completely determined by that state function. So the problem in quantum mechanics actually how to find that state function. Why? Because if we know that state function, actually we know completely the information of the system. In linear algebra, this state function actually is a vector. So we know in linear algebra, if we have an arbitrary vector, principally we can expand it, this vector, into many bases. Bases characterize the dimension of the system. So if we talk about the n dimension of that state space, so principally we can construct n basis vector. If we know that it is a vector, we can represent everything about the vector in this space into this basis. This is the so-called the superposition. In quantum physics, we customize follow direct notation. The unit vector is called the cat, denoted by the form. Correspondingly, the cat is conjugate transpose is bra. So the inner product can be represented as the bracket, shortly bracket operation to form the scalar value. For example, a qubit, a quantum bit in simple form, for example, is qubit is represented by spin half. So spin up will be represented as zero value, 0 bit. and spin down is represented by 1 bit. Yeah. So a quantum bit in two-dimensional state space governed by the superposition of two bases. Denoted by 1 and 0, like in classical bit, 0 and 1. So principally, bracket notation of a qubit or a bit which represent everything completely in this two-dimensional state can be written as A and 0 plus B cat 1. Because of the unit vector, that's why A square plus B square should be 1. There is a physical meaning of this, but we can postpone right now. Some simple metric operation, for example, the cat 0 can be represented as a metric 1 0, and bra, the conjugate transpose of this cat, by row metric 1 0, and cat 1 by 0 1. So by this representation, we know this is actually a basis because they satisfy the orthonormal property. For example, if we took the inner product of bracket of 0 and 0 will be 1, just simple operation. Bracket of 0 and 1 will be 0, 0 and 1 0, but 1 and 1 is 1. That's why when we talk about a qubit and took the inner product of this qubit, we get that the cat of qubit can be superposed to its basis because of their bases are orthonormal. That's why we obtain the value of 1. In quantum physics, following Born interpretation, we call this inner product as a measurement entity. We call it the total probability to find a particle in this whole space, in this two-dimensional space. So the inner product of the state or the bracket of the qubit will represent that in this two-dimensional space there will be surely 100% 1 qubit because we got the value of 1. So the inner product of that state actually measurable. We can prove it in experiment. We know in algebra that the basis is not unique. We can choose other bases. For example, in this qubit, we can represent cat as cat represent up direction, and cat by direction. to differentiate with that this we represent as, and the other cat can be written as this value, SN and B, actually can be picturized as the two-dimensional space. We call this one orthogonal as 0. But this one, actually, we can rotate this basis into the new configuration. For example, in 45 degree, here in 45 degree. So this represents the cat, and this represents the cat. By rotation procedure in metric, we know that this actually causes. So we can choose any arbitrary basis to represent this qubit, any qubit. This is postulate 1. Postulate 2 concerning time evolution. The time evolution of any closed quantum system, or a cat state, is described by the so-called the Schrödinger equation. That's actually the differential equation, first order in time and second order in space. So the form of this equation rather similar with the wave equation. That's why in that time we call this Schrödinger equation as a wave equation in quantum scale. The solution of this equation, we call it the wave function, not wave classical, but in different character. The wave function here can be represented by any complex function in a state space. In quantum computing, we usually prefer to use another form, the so-called Heisenberg picture, not Schrödinger equation. Actually, this is the integral representation of the Schrödinger equation. So we can transform the Schrödinger equation into the Heisenberg picture. In quantum computing, we prefer this notation because when we know that this by postulate 1 represent the any complete information of that system in certain time, this state can be obtained by the state space in initial time by the transformation which we call the evolution operator. So in quantum computing, we prefer this form because this can represent the device. This is the quantum computer. So these transformations can be represented by quantum gate. We know that the classical computer actually based on the some fundamental or Boolean operation, and or etc. So in quantum mechanics, by this presentation, we hope we can construct the quantum and quantum or and etc. to form the quantum device. But we know the property of this operator is unitary operator. What is the implication of this operator? By definition, the unitary operator defined by that relation. It means in quantum physics, if we want the information, it should be real. In quantum system, we can take the inner product of this state. So the inner product of wave function or cat in arbitrary time can be written as this. But the state in any time is the result of the transformation of the initial time by the unitary operator. That's why we can write yes. Yeah. Complex here, complex space. What you mean? Uh, uh, uh. Yes, complex. Generally complex metric. Yeah. Yes, actually, this is in in the term of postulate 2. Here is just in general idea. There is no restriction about this type of the operator. Yeah. We can analyze this operator when we try to operate for certain purpose. Yeah. When we want, for example, the NOT operation. Yeah. If the initial gate is 1, by NOT operation, we try to find the zero state. If the initial condition is zero state, we try to change into one state. So if we want this kind of spatial operation, we can construct the spatial gate of not operation, and then we can check whether this satisfy the unitary operator. It's just postulate. Just a statement. There is no need to find why that is unitary. Just postulate, and by that postulate, it's beneficial for to describe the microscopic space. Yeah. Just statement. Yeah. It's difficult. That's why this is just the illustration. Yeah. Generally there is no direct relation. When we know the gate in classical computing, yeah, and then we can automatically construct the analogy of that gate in quantum computing, because there is restriction of this operator. Yeah. For example, if we took the inner product of this arbitrary state, yeah, it means because of the unitary operator, it is equal to the initial inner product. Basically, this means that even though the time is different, but the inner product of the initial state and outer state preserved. And because of the property of unitary, not only preserved, but also reversible. So we can take from any t to initial state, also from initial state to any time. It should be preserved and reversible. This is the difficult part, to construct the kit, the quantum kit, because of this. Because it must follow the postulate of quantum physics, not classical physics. Postulate 3. The every observable correspond to any observable, realistic observable, must be Hermitian operator. For example, if we want the observable of momentum, in quantum physics, we must construct the mathematical operation of this observable. The mathematical operation which corresponds to the Hermitian property of this operator can be written as minus EH bar dDA. The expectation value of measurement on any observable can be taken as the operation of bra and cat, but in the middle of the bra and cat, we must operate first the cat. So basically, this operation very strict. Yeah. We cannot change the operation to the cat, yeah, and to the bra. Why? Because not mathematical operation is Hermitian. We can interchange that form if the operator O is Hermitian, by definition. Because by definition, we call the Hermitian operator when that form is the same. What is the implication of this operator in quantum computing? When we have the base, for example, 0 and 1, and this base by the linear algebra actually can be related to the function, eigenfunction, and eigenvalue. Suppose we have the eigenvalue relation when the O operation operate to get C1 or the first base, we get the eigenvalue O1, and then that base behavior. Also in the second base. By postulate 3, if we want the value of the measurement, we must operate the expectation value. When this form of base satisfies the eigenvalue, we know that the expectation value is equal to the eigenvalue. But when the unit vector ket is not the eigenvalue problem in two-dimensional state, so basically we can superpose that ket into the base, like previous example. That's why the expectation value can be expanded into that base. Because in that base satisfying the eigenvalue product, that's why we obtain that the expectation of O is not the same with the eigenvalue, but the same with the eigenvalue of the first observable times the A square, and then the second observable times B square. That's why we know that the coefficient of the superposition in physical point of view represent the probability to find that measurement. A equal to the probability to get the observable O1. B square equal the probability to get the observable B. So in quantum mechanics, we can expect the result just in probability expectation, not deterministic. So this is in some ways can be pictured as every measurement always disturb the system. Because in quantum physics, every measurement actually the operation of some kind of model, whether it satisfies the eigenvalue or doesn't satisfy the eigenvalue. If satisfy, it means the expectation value equal to the eigenvalue. If no, the expectation value just the probability of that many eigenvalues. postulate 4, if we have many qubits to form a single system, in order to construct the configuration of many special kits to form the certain device, we can relate this composition by the so-called tensor product. If the state is not entangled, is not correlated with the other, then the whole state can be represented as a tensor product of the individual state. But if many qubits has many correlation with the other, we cannot represent it as a tensor product. For example, we have a system of two qubits. Every qubit can be represented as get 0 and 1 as previously slide. If two qubits are not entangled, then we can represent the whole state. One qubit stay in two-dimensional space, and two qubits stay in four-dimensional space. That's a consequence of the tensor product, bimetric like previously given. That's why the representation of the C12 two qubit can be given as 4 bases: 0, 0, 0, 1, 1, 0, 1, 1. A1, A2, as previously, postulate 3, represent the probability to find the observable which satisfy the eigenvalue to 0, 0 ket. But when two qubits are entangled, we cannot represent it as a tensor product. For example, we can represent this two qubit system by just superposition of ket 0, 0 and 1, 1. This is just example. Why this kind of superposition? Because by choosing this superposition, it is not possible for us to decompose into two tensor product. This is one of the form entangled into code. We also can choose the other entangle is 0, 1 and 1, 0. That's also is cannot be composed into two tensor product. What is the importance of this entanglement system? In this kind of state, in entangled system, a measurement of one bit is always influence another bit. This is the first qubit. This is the first qubit. This is the second qubit. With the probability to get the 0 and 1 bit. By this representation, we can take the experiment to first qubit and get 0, for example. Because of this, if we got the 0, it means the probability to find that 0 for first bit is a square, like in previous example. So the next state will be collapsed into 0, 0. The 1, 1 disappear. It means this implied because of the state collapse to 0, 0, the second bit is also 0. So there is no need to measure the second bit, because when we take the measurement to the first bit, it will give influence to the second bit. The possibility to use this phenomena is to ensure that there is no eavesdrop, there is no spy in transmission of information. Because when there is someone try to spy the information in quantum physics, it means there is a disturbance, there is a measurement. If the spy exists, and then the last operation will know that the result will be different with the expected. Why? Because the existence of the eavesdrop, the spy, will disturb the system. The action of the spy will give the additional a square to the system. So the final person will always know whether there is a intrusion or not. In classical physics, because of the experiment or measurement principally can be minimized. That's why the spy, the eavesdrop, can try to make this disturbance as small as possible, so cannot be detected. But in quantum physics, because of the observer is insider of the system, every effort to disturb the system, the other measurement will collapse to the other state. So the error correction, teleportation, codance, and Islam can be rooted by this phenomena. I think it's finished. What I talked today, and thank you.
Okay, thank you for Dr. Pekik for the lecture. And Dr. Pekik, please stay on stage. There is a souvenir from the committee. May I invite Dr. Indah Emilia to come to the stage and offer a souvenir to the speaker. Okay, this is the end of the first session, and the next agenda is coffee break for 30 minutes, and enjoy your food in there, so you can go there now. Okay, thank you.